Bismillahirrahmanirrahim. Hello students, welcome to the Electrical Engineering channel. In this lecture, we are going to discuss the third chapter of the Engineering Electromagnetics book, and the name of this chapter is Electric Flux Density, Gauss's Law and Divergence Theorem. So, the first topic of this chapter is Faraday's experiment, and Michael Faraday actually performed an experiment in which he used a sphere, and on the surface of the sphere he deposited a plus q amount of total charge, and he also took two hemispheres of bigger radii, and he just clamped those uncharged hemispheres outside this inner sphere, and the overall assembly after the clamping looked like the one which is shown in this figure. Okay, so at the center we have smaller sphere, and at the outer surface we have a bigger sphere. Its radius is bigger, but the inner sphere had a positive q charge, and the outer sphere was uncharged initially. So after some time, equal amount of negative charge actually deposited on the outer surface. So this phenomena showed presence of some field, and that field was called as flux between inner and outer sphere. So these are called flux lines, and you can see the direction of these flux lines, which are going radially outward from the inner sphere or from the center. And the amount of the flux is actually exactly equal to the charge enclosed, right? So this is a closed surface, which is the outer sphere, and the total amount of flux leaving out this closed surface is equal to the charge enclosed by that closed surface. uh, okay, so we have to first calculate the flux density. Okay, so these are the flux lines. So the density of these flux lines can be calculated by simply dividing this flux with the surface area of the sphere. So it is equal to psi divided by 4 pi r square, and AR is a unit vector, which is the radially outward drawn unit vector. So psi is the flux, and psi is equal to q. So q is over 4 pi r square. AR is actually the flux density. So initially psi is actually proportional to q, but the constant of proportionality has a magnitude of 1, so psi is equal to q. So later on I will show you that this is actually the statement of Gauss's law, that net flux leaving out the closed surface is exactly equal to the charge enclosed. Okay, so I will discuss later. And d is equal to q over 4 pi a square ar. This is the flux density at the inner surface, and this is the flux density at the outer surface. And one more thing is that you can see d is equal to q over 4 pi r square ar, and it is independent of any material characteristic, right? So for example, in electric field intensity we saw epsilon over here. So electric field intensity is dependent on the permittivity of the medium, but electric flux density is independent of the medium. So it means that if we have a plus q charge at the inner sphere, and whatever medium is present between these two spheres, after some time equal amount of negative charge will eventually be induced at the outer surface. It means whatever is the medium between them, electric flux lines will be same, and electric flux lines actually don't depend on the medium. So that's why we don't see any quantity or any symbol for the medium, right? So this is E, this is expression for electric field intensity, and by comparing these two expressions, equation 1 and equation 2, we can say that D is equal to epsilon E. So if we have a volume charge, then D will be equal to rho V dV divided by 4 pi r square AR, and we will use a triple integral or volume integral over here, right? If we have a line charge, then D will be equal to rho L over 2 pi rho A rho, and the since d is equal to epsilon e for electric field intensity, this was equal to rho l over 2 pi epsilon rho, but for d there will be no epsilon in the denominator. Similarly, for surface charge distribution, d is equal to rho s over 2 a rho, or In case of electric field intensity, this expression was equal to rho s over 2 epsilon. So these are the expressions for electric flux density and electric field intensity, and their magnitudes are actually related to each other by this epsilon term, and their unit vectors or their orientation is the same as that for electric field intensity for all the types of charge distributions. Either it's a point charge, volume charge, line charge, or a surface charge. Now I will solve couple of examples to get a deeper insight into the electric flux density discussion. So in this example, we are given a point charge of 60 microcoulomb, and uh, we are also given the radius of the spherical surface, and it is equal to 26 centimeters, right? So this point charge is actually located at the origin, and we have to find out the electric flux density at this spherical surface. So this is a partial spherical surface whose radius is equal to 26 centimeters. Theta varies from 0 to pi by 2, and phi also varies from 0 to pi by 2. So let's first calculate the total flux, and a total flux is equal to d dot ds, right? And d is equal to q over 4 pi r square, right? So this is actually q, and this is 4 by r square. So this is the electric flux density. Now we have to find out the flux leaving out this spherical surface. So this will be equal to d multiplied by ds, and the ds is equal to r square sine theta d theta d phi, which is a spherical surface, and we know all the quantities. So just we have to evaluate the surface integration, and then we will get our answer. Now, in the second part, we have to find out the flux leaving by the closed surface defined by a rho equal to 26 centimeters and z is equal to plus minus 26 centimeters. So this is a closed cylindrical surface, right? Again, the point charge is located at the origin as was in the first case. So here you can see this is the origin where we have the point charge, and this is the closed cylindrical surface, and we have to calculate total flux leaving out this closed surface. Now we know that total flux leaving out any closed surface is equal to the charge enclosed. So the total flux in this case will be equal to the amount of charge, which is 60 microcoulomb. So this is very simple. There is no need for the solution. But in this case, actually, we didn't have a closed surface. So this was actually a partial spherical surface, or we can say differential surface of a sphere. It wasn't a complete closed surface of the sphere. So that's why we needed this calculation. But here we are already given the closed surface, so the net flux is equal to the net charge. In the third part, we have to calculate the flux leaving this plane, which is located at z equal to 26 centimeters, and here at the origin we have the point charge. Now this is an infinite plane located at z is equal to 26 centimeters, and we have the point charge over here, and this plane is extended up to y from minus infinity to infinity and x from minus infinity to plus infinity. So the total flux leaving out this closed surface can be divided into two parts. First part is actually moving in the positive z direction, and one part is flowing towards the negative z direction. So the part which is moving in the positive z direction will actually be the part which will be passing through this infinite plane, and the rest of the negative charge will never cross this plane, right? So the flux in the negative z direction will never cross this plane or this surface, but the flux which is in the positive z direction or in the upward direction will eventually cross this infinite plane, right? So half of the flux will pass through this plane, and half of the flux will be equal to half of the charge. So it is equal to q by 2, and it is equal to 30 microcoulomb. So I hope that was a self-explanatory example. So now I am moving towards Gauss's law, and Gauss's law can be stated as the electric flux passing through any closed surface is equal to the total charge enclosed by that surface. And mathematically, psi is equal to q, which I already demonstrated before. And mathematically, these are our set of point charges, and this is our entire volume, and at this point we actually want to calculate the flux leaving out this differential surface or incremental surface, right? So this is point P, and around that point P we have marked an incremental surface delta S, and the net flux passing through this incremental surface has to be calculated actually, right? So first we can calculate the density, the flux density, right? So if we are given the flux density and we are given this incremental surface, then we can calculate the total flux. So this is our differential or incremental surface delta S, and the radially outward drawn normal at the surface will be the direction of this delta S. So this is delta S, and this is the direction of delta S, or the unit vector of delta S, and the direction of the electric flux density is actually radially outward from the source. So source is located over here. So looking at this source of point charges, we have to mark the direction of the electric flux density. So it will be in this direction, right? So looking at these sources, the direction of electric flux density will be in this direction. So the total flux which is leaving this certain incremental surface delta S will be the dot product of this delta S and this electric flux density. So delta phi is equal to flux crossing delta S, and the flux crossing delta S is equal to ds cos theta multiplied by delta S. So this is ds, and this ds has two components. This component is ds cos theta, and this component is ds sin theta. Theta is this angle between ds and delta S, and ds cos theta is actually the component of electric flux density which is in the direction of delta S. So this component will be used, and it will be equal to d dot ds. So this can be written as d dot ds or d dot delta S. So total flux is the integral of this ds dot delta S, and it will become ds dot ds closed surface integral, and this circle actually corresponds to the integral evaluated at closed surface, and it is also equal to charge. Flux is equal to charge, so charge is equal to d dot ds. Now this is also flux. This is also flux if we have a volume charge distribution as in this case. So by comparing these two equations, we can say that d dot ds is equal to rho v dv, and this is closed surface integral and this is volume integral. So d dot ds is equal to rho v dv, and this is called divergence theorem, which I will also explain you in detail in the coming lectures. So that is all about our today's lecture. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.